donc au département de sciences de l'ingénieur. Et Laurence a bien accepté de venir parler de micromécanique, de réseaux polymériques quasi idéaux. Et voilà, je lui laisse la parole. Merci Laurence.
Merci beaucoup Justin. I will switch to English if it's okay. So thank you very much for inviting me. That's a great pleasure to be here. And today I would like to present some work that my PhD student at Monash did really. So Gadir, she's finishing her PhD at Monash University, where I was just before joining Oxford a bit more than a year ago. And so we started working on this problem of mechanics of hydrogels, really. That was the background, hydrogels, which are polymer networks swollen in water. And the idea was to understand a bit better the relationships between network architecture and mechanical properties. And we will focus on a special type of hydrogels, which are called this ideal network hydrogel. So this is where this near ideal network is coming from, but I will explain that just after. So we are talking about hydrogels, which I'm sure you know are polymer networks swollen by a large amount of water. And this is the classical cartoon you will see from people talking about hydrogels. So you have some polymer chains that are linked together by cross-linking points, some junctions, chemical cross-links in our case. And you have the water. So the idea is that the presence of this cross-linking point prevent the network to dissolve and confer the network some elasticity. And these hydrogels, they have a lot of applications. Some are very traditional applications like contact lenses or wound dressing. You can find hydrogels are super absorbent in diapers, and you can also buy this little cool colored beads that you can swirl yourself in water if you want. So, and as you can realize from these examples, these are very fragile and weak materials. And at the same time, there is a realization that the mechanical properties are directly linked to the network architecture. And so the idea is that how can we tune or design the architecture of the polymer network so that we can improve the mechanical properties of the gels in terms of stiffness, strength, toughness, and there are a lot of work nowadays of different groups trying to make new kinds of gel by proposing new architectures to have these properties. So if we want to be a bit more realistic about what the polymer network might look like, this is probably a bit more what it is. So in reality, in most of the hydrogel network you have, just or polymer in general, that will be more like a messy arrangement of chains with a lot of defects in a broad sense. So by defect, we mean, for example, the fact that you may have an inhomogeneous distribution of the crosslinks. So for example, you may have regions of the network that have more or less crosslink. So that's one non-ideality. You also have topological defects. So for example, you might have chains that are only linked by one end. And so effectively, this chain do not contribute to the elasticity of the network. So these dangling chains, that's one type. We also talk about loops. So the loops are found when you can basically go from one crosslink and back to the same cross-linking point along one chain. That would be a first-degree loop. So that loop will be also elastically ineffective. But you can have second-degree loop, for example, when you have two chains linking the two same crosslinks, so you can go back and forth along two chains, and third-degree loop, etc. And you have also entanglements, which kind of play the role of a crosslink, but maybe a temporary one, and that's also a sort of defect. So the idea is that, okay, can we control or maybe minimize the presence of this defect in order to have maybe better mechanical properties? And this is really the idea that has been pursued by a group of researchers in Japan, led by Sakai, who came up with the idea of these ideal hydrogel networks but maybe more than 10 years ago. So what they did is making hydrogels by combining well-defined macromolecules in solution. So they start with this four-armed macromolecule. So you have four branches with a well-defined number of monomers along each arm. And you will have two types of these macromolecules, and each type has a different functionalization at the end of the arm, so that you can cross-link or you can couple the two macromolecules because the end group will react with each other. And you will do so also by preventing self-reaction. So you prevent two arms from the same macromolecule to react with each other. So you prevent the creation of this first degrees loop. Yeah, so that's the idea of this tetra-PEG. PEG is the name of the polymer that is used to make these big macromolecules, and that's widely used for biomedical applications. So they make this four-arm PEG hydrogel network, and they are assumed, or they are thought to be almost perfect, in the sense that you don't have any entanglements in these gels, you don't have first degrees loop, and there is a high degree of reaction between the arms. So you also minimize the amount of dangling chains in these gels. And one evidence for this is the good mechanical properties you can get. So this plot shows the compression response from this sort of gels compared to more traditional synthetic hydrogel or natural gels. And basically you can get a much higher compressive strength of the order of megapascal. So not only it's interesting for the application because you can make stiffer and stronger gels, but also from a fundamental perspective, it's also an interesting system to study, because then you can start to make modeling with a better knowledge of what the network structure is, and that's convenient for the modeling point of view. So we wanted to use this this type of hydrogel as a model system to start looking into structure properties relationships in polymer networks. Now, even though they are almost perfect and they have good mechanical properties, they are still not perfect. So there still is some defects. So the first class of defects you may find in these gels is still the presence of some unreacted arms or dangling chains. Even though the reaction efficiency is quite high, you still have some amount of these unreacted arms. Now, the good news is that the same group of researchers have also found a way to tune the amount of these unreacted arms. So not only you can measure the reaction efficiency, so the proportion of the arms that have reacted with each other, but you can also control that. So what they did in this particular case is pre-degraded the gels or the pre-polymer so that you deactivate some of the reactive end groups, and you can control then the reaction efficiency of your system. So you can go from 90% or above, so very almost perfect network, down to something like 60%. So we have this information. We would like to take into account this reaction efficiency, this P parameter. The second type of defect is the presence of second-degree loops. So these are the loops you find when you have two arms or two branches linking the two same cross-linking points or junctions. So these are a bit trickier to investigate because it's more difficult to measure experimentally and very hard to control as well. And also very few reports say something about the loops, so we don't really know how many there are in the gels. There are a few reports still who try to measure and quantify the amount of loops in this tetra-PEG gel. So this is an example where people have measured by NMR the fraction of double links or triple links you may find. What I just want to say here is that what they found is that the fraction of loops decreases when the concentration of the pre-polymer increases. And when you go to low concentration, like near the overlap concentration, let's say, you may find as much as 50% of chains that participate to double links or second order loops. So the loop fraction can be quite significant. And so we would like to understand what's the effect of loops on the mechanical properties. So what we want to do in this work is address this problem using a micromechanical approach. So as always, we start then by the constituents, here the individual polymer chains, and we try to assemble them in a network, in a model network, and get up to the mechanical properties of the whole network. So starting from the single chain, we started by considering maybe one of the most popular and simple model out there, valid for large deformations, which is the fully jointed chain model for ideal chains. So you represent your polymer chain by an assembly of, well, n links of the Kuhn length B. And then you can get the force extension relationship following classical statistical mechanics treatment, which gives you the force extension relationship following this inverse Langevin relationship. So basically what it says is that when the extension is small, at small forces, you tend towards a linear force extension relationship, which recovers the Gaussian chain behavior. But as you go to large stretches and you approach the contour length, which is simply the number of Kuhn segments times their length, then the force tends to infinity. And so there are well-known expressions for that, for the free energy of the chain and the force extension relationship. So we use that as a starting point. The question for us really is how to deal with the network. So we looked, of course, in the literature for rubber elasticity theory, where there are a lot of micromechanics inspired approaches to deal with networks. And I'm sure you're familiar with all these well-known models. So, for example, the three-chain model, where you would have three representative chains aligned with the principal stretches direction. Then you can deform your little representative cube, or the three principal stretches, and that allows you to calculate the energy in each chain. Then you can sum that up to get the free energy of your network. And you have other types of assemblies that sample the orientation space, such as the 8-chain model, the Arruda-Boyce model, or the full network model, or all this microsphere type of approach, where you really sample the entire orientation space. And most of these models will assume purely affine deformation. So you basically deform each chain following the same macroscopic deformation gradient that's given. So once you have calculated your stretches in each chain in your distribution, then you can calculate the free energy of the network by summing up or averaging the free energies in all the chains. That gives you the force extension relationship. So there are a few limitations that are well known to this type of approach. Well, they can give you a realistic stress strain curve, but usually you need to fit the parameters in this model. So even if the parameters have some physical basis, it's still very difficult to really relate them to the actual parameters of your system. There are still some limitation in getting good prediction under different types of loading. So if you fit the model on uniaxial tension, it's not guaranteed it will work for biaxial tension or shear. And the third limitation, which is directly relevant to us, is the fact that, as you can see, it's not going to be possible to incorporate a description of the defects, of the loops, or the unreacted arm. It's not straightforward to incorporate this into this simplified representation of the network. So what we did in our work is follow the same philosophy, so the same treatment of single chain and assembling chains in a network, but we do this like more the RVE kind of approach, where you actually represent a network with a collection of chain in a discrete way. So we have these big assemblies of chains with a defined topology, and each chain in the network is described by its force extension relationship given by the fully jointed chain model. And we have this sort of representative volume elements that we deform by applying affine boundary conditions. So we prescribe the displacement of the boundary nodes based on the given macroscopic deformation gradient. But then, and that's the difference with the other models, we calculate the position, the equilibrium position of the internal nodes by force balance or energy minimization, and this is done using lamps. And then when it's done, then we can calculate the macroscopic stress based on the reaction force on the boundary nodes. So that gives us our force extension relationship, or the deformation gradient versus stress. In terms of the topology and the network we created, what we did is, because we have in mind these tetrapeg hydrogels, so we wanted to have coordination of 4 at the cross-linking points, and or lower if they are unreacted chain and then they do not participate to the elasticity. So what we did is we started with unstructured tetrahedral finite element mesh, randomized, etc. And we position the junction point at the center of each tetrahedron and link 2 junctions through the common faces of 2 elements. So that guarantees that you have a coordination of 4 at each junction. And that creates the perfect network, which we start from. And then based on that, we introduce defects in a second stage. So what we'll do is we will randomly cut off some of the bonds or the chains with some probability that corresponds to the reaction efficiency, this P parameter. And we also introduce loops. So for the loops, what we do is we consider 2 pairs of adjacent crosslinks and cut them off, and we assign them so that we create 2 double links each time. So we have a way to control the reaction efficiency and the loop fractions in our system. So the parameters the input we have then is the chain behavior. So we use the fully jointed chain model, but that bit could be changed by some other theory like a worm-like chain or whatever. But for the fully jointed chain, the 2 parameters you have will be the number of Kuhn segment and the Kuhn length. And in terms of structure, we can play with the density of elastically effective chains. So here, this n is the number of springs in the network. And this is more like a numerical simulation parameter. So we choose this number to be very large so that the network is statistically representative and the results are converged. And that means that for a given density we aim for, we change the density. Well, we reach this density by actually adjusting the length of the simulation domain. So we start from a network and we basically contract it or expand it to get the density of chains that we want. The second structure parameter we use is the average crosslink coordination, this Z here, which is directly linked to the reaction efficiency. So as you start cutting off some of the springs or the bonds between the cross-linking point, then the coordination decreases, and that slightly depends on the loop fraction as well, but roughly it's almost one-to-one relationship between coordination and reaction efficiency. And then we have the loop fraction, so the fraction of the chains that participate to double links or triple links. We may have quadruple links, but this one, they do not contribute at all to the elasticity and they are just removed. So the question for this study is really how do the elastic properties vary when we change these parameters, and we want to do it in a very systematic way and really see if we can get some scaling relationship, for example. So we started by the elastic modulus, so the initial slope of your uniaxial stress strain curve. And so we simply, change one parameter and keep the other constant and see what happens, basically. So if you plot the normalized elastic modulus as a function of density, you find a scaling with a power of 1/3. And the modulus depends on the average coordination. So these are for networks with no loops, but we have the same sort of results if there are loops as well. So denser networks have a bit stiffer response, but if you're familiar with rubber elasticity theory, then you can already flag that this is not the exponent that you would maybe expect, and I'll come back to that. And it also shows that when the coordination lowers at constant density, you have also a softer response. This one shows that both the coordination and the loop fraction have an impact. So this is for constant density and changing the coordination, but for different loop fraction. And what's interesting here is really to show that when you go from a network with no loops and you go like to 40% loops, let's say, you really have a sharp drop in the stiffness. So the loops do have a very strong impact on the elastic response. So to try to make a bit more sense of that, we wanted to get some scaling relation and try to interpret these. We can get a nice collapse of the modulus as a function of coordination and loops, provided that we plot everything as a function of the coordination minus the critical coordination. So that's the coordination at which you start to lose percolate. It does not percolate anymore. And this depends on the loop fraction. So it's like shifting all the curves, and then all the curves for different loop fraction collapse on a single line. And you can describe this relationship by this scaling relation that embodies a bit of everything. So we found that the elastic modulus is inversely proportional to the number of Kuhn segments. It's to the density to the power 1/3, and depends on coordination, and the loop fraction is lumped into this critical coordination here. So that's the scaling we found numerically. So how can we explain this, in particular, maybe the unexpected power in the density we see here? So for this, we started by an exact analytical expression for the elastic modulus for a network of Gaussian chains, because at small stretches, which is the case when you calculate the elastic modulus, all the chains are in their Gaussian regime, so you can use result for a network of Gaussian chains. And the result is the following. So normally the elastic modulus is kt nu, but there is an extra factor that is often forgotten, which says that it's also proportional to the ratio of the square initial end-to-end distance of the chains in the network divided by the root mean square distance squared. So now you can see that if in the network, in the initial states, all the chains, or on average, the chains have their random walk distance. So if this R is square root NB, then this factor becomes 1, and you recover your classical affine model where the modulus is simply kt nu, and the modulus is proportional to the density of elastically effective chain, which is what a lot of people use. But the thing is that in all simulations, we cannot enforce the end-to-end distance of the chains between two cross-link points, because this will depend on the topology of the network. And this is all coupled via the equilibrium equation. So R is not something we prescribe, it is a result of the simulation, and it's in general not equal to square root NB. So in general, we have another factor here, which depends on density and depends on coordination and loop fraction. So all the effect of defects in topology goes into this factor, which is a measure of the pre-stretch, really. So what it shows is how extended or compressed are the chains in the original network before you even start deforming it. So we call it the pre-stretch. Now, if we look at how this pre-stretch or this R changes with topology, we can also do a bit of scaling, and this one is really following geometry. So for example, this is the scaling we get for the initial end-to-end distance as a function of density and coordination. It all collapses on a single curve again, provided that you plot it as a function of this z minus zc, where the loop fraction is hidden. And this one really can be explained on geometry. So if you remember, the density really governs the length scale of the simulation domain. So you have a direct relationship between density and this initial R. So the more dense the network, the more compressed the chain are, which makes sense. And also the coordination dictates the volume between cross-linking points, and you can also get that relationship from geometric argument. So that all works well. If we have the scaling, we put it back into the exact expression, and we recover the scaling on the previous slide. But so what I really want to emphasize here is that you only recover the classical affine estimate when the pre-stretch is equal to the random walk estimate, and that's not the case for us. And we also don't think it should be used for this sort of ideal network gels, because in these gels, the length of the arm, the number of Kuhn segments is set from the outset, from the pre-polymer structure. Whereas in the affine model, what's assumed is that the end that you see here is actually in a vulcanized network, for example. This end would be the average number of segments you would find between crosslink after you have created this crosslink, and then it makes sense to say the end-to-end distance will be the same as the random walk estimate. But for this tetraplex gel, we don't think this is necessarily a valid assumption. So that's for the modulus and the emphasis on the effect of pre-stretch of the chains on the value of the modulus of the gels. So we also looked at the limit extensibility, so the stretch when you do uniaxial tension, the stretch at which the forces reach to infinity. We also have a measure for that, which we got directly from the network without even having to do any simulation. Actually, what we do is we calculate the shortest path between two boundaries of the RVE and postulate that the extensibility is reached when the shortest path across the network reach the n times the contour length, basically. And we found that this is a very good approximation of the actual limit when the force tends to infinity. So we use that measure. In terms of numerical result, you find that the maximum extensibility also scales with this new power 1/3, which is for the same reason of pre-compressed chains, and also changed with coordination. We also looked at the effect of extensibility in terms of coordination and loop fraction. So here it's a bit more complicated to understand how the loops will affect the extensibility. There's a crossover. So at high coordination, having more loops will decrease the extensibility, but at low coordination, having more loops will increase the extensibility. So there's not a clear tendency. To try to understand this, we started from a very simple estimate of the maximum extensibility, which is taking a representative chain aligned with the loading direction and say that extensibility is reached when the contour length, when the lambda, when it's equal to NB over R, and R being again this initial end-to-end distance of the chain in the network. If we substitute for R the scaling relation we found previously, then we have an estimate for the extensibility as a function of network parameters, so density, coordination, and loop fraction via this critical coordination here. That works well for the effect of coordination and density. That doesn't work well for the loop fraction. So this one we still don't really know. There's some so it's not only via the pre-stretch. We think that the presence of loop will affect the shortest path, and that must be something along this line, more subtle effect of loop fraction on topology that's not captured by just the pre-stretch relationship. So that's what we did for getting some scaling relationship. We also wanted to use this sort of numerical simulations to evaluate the accuracy of mean field or continuum rubber elasticity models. So what we did is look at the stress strain curves and compare the prediction to the 3-chain model, the 8-chain model, and the full network model, which are 3 popular rubber elasticity theories. So of course the comparison only makes sense if we use the same input parameters, but also if we pay attention to the pre-stretch, because of course we know that in our simulation the behavior will depend on the pre-stretch. So we had to revisit these 3 analytical theories to account for a pre-stretch that's not necessarily given by the random walk estimate, and have a bit more generalized version of these 3 models and compare them only when the chains have the same pre-stretch initially, so that you get the correct slope by construction. Because these 3 models all predict the same affine modulus estimates. So they are the same in terms of the initial modulus, but they will differ in terms of extensibility and stiffening behavior. So this is the response, the comparison we see in 3 loading directions. In all cases, it's really the full network model that is the best, clearly, and the 8-chain model is always an underestimation. The full network model is slightly less accurate for biaxial loading, but that's quite minor. Now, in terms of the reasons for the discrepancy between these models and the discrete network model we have, it might be due to, of course, the sampling of the orientation of the chains. It might be due to the distribution of the pre-stretches, which is there is a distribution, as I will show, and there's also the question of affine deformation or not. So if I start with the distribution of the chain length, this shows the distribution of the initial chain end-to-end distances in the network with the different models. So we have the discrete model, which is almost a Gaussian distribution, and here we have set the density so that the initial end-to-end distance is on average equal to the square root NB. So this is the initial distribution of chain end-to-end distances, and all the three other models assume that all the chains in the network start from the same initial state of pre-stretching. So we have just a single line. Then as we start to deform the network, well, we have a distribution of chain end-to-end distances. So again, the black line is, now here's the blue line becomes actually the discrete models. You can see how the distribution flattens as you stretch the network. So this is for 3 different macroscopic stretches, and you see how the distribution changes. So the 3-chain model will have, well, one chain is extended in the principal direction, and the other 2 have the same corresponding stretch. Then the 8-chain model, they all have the same initial and the same end-to-end distance, and the full network is the only one who also predicts a distribution of end-to-end distance as we stretch the network, and it kind of follows the distribution from the computational model. The only difference we see really is in biaxial, which is the case where the full network model is slightly less accurate. Well, in biaxial loading, this is also where we see there is a discrepancy between the distribution of chain stretches in the full network model and in the discrete model. The full network model misses some of the highly extended chains, which seems to be the reason why it's a bit softer than the reference solution. Now there's this question of affinity. So in the rubber elasticity literature, people try sometimes to improve the prediction of rubber elasticity models by addressing this affinity question, because there is no reason or why the chain would still deform affinely at large deformations where the force extension relationship is non-linear. So we wanted to see whether that was happening in our network. So what we did here is starting from the initial distribution of chain end-to-end distances when there is no applied deformation, and we deform the network, and we compare 2 things. We compare the actual distribution that we find by solving the equilibrium equations, and we compare that to the distribution we would get if we apply the same macroscopic deformation gradient to each chain in the discrete network. So we enforce affinity of deformation at each chain, and so do not satisfy equilibrium. What we see is that there's very little difference between these 2 cases. And another way to look at it is simply propose a measure of deviation from affinity. Here we use the average of the difference between the actual and the affine end-to-end distance normalized. And we did that for different presence of defects. And basically, this deviation from affinity is very small. So it's of the order of a few % at most. So it looks like loss of affinity is not really a thing in this highly idealized network, at least. Now, for the last part of the talk, I just want to briefly show you some comparison between our simulations to actual experimental results for these tetrapec hydrogels. So here, the challenge is, of course, to be able to identify the input parameters from the experimental conditions. Luckily, we don't have so many things to identify, but there are a few challenges here still. So what we know from the preparation conditions, what's reported in the literature, in the experimental literature, is the volume fraction of the pre-polymer. So this 4-armed PEG macromolecule, so we know that. We also know their molecular weight, from which we can calculate the number of monomer we have in each arm of the tetrapec macromolecule, which we multiply by 2 because the number of monomers that's here is the number of monomers that there will be in a chain in the network, which correspond to 2 arms. And we also have an estimate for the contour length of this PEG using this projected length of the monomer in the TTG configuration. So this is based on literature as well. So this is what we use and what we consider to be known. One challenge we found is that there is evidence that these PEG chains in solution, they do not behave as ideal chain. And so there are some experimental reports that from the same group of researchers that show that if you put in solutions all these 4-arm macromolecules and you prevent them from reacting with each other, for example, you have this A-type and B-type macromolecule, you just put the A-type together, so they can't react, but you change the concentration of this macromolecule, what you see is that they will basically contract, pre-compress by themselves. Not creating any entanglement whatsoever, they will just, the gyration radius will shrink as the concentration increases. So which means that the end-to-end distance of the free chain is a function of concentration, which is non-ideal behavior. The scaling for this gyration radius, also in terms of number of Kuhn segments or number of monomers, is also not following literature or classical scaling relationship for ideal chains. So this is just showing the gyration radius as a function of preparation volume fraction for different molecular weights and showing the evolution of this. So we have this, which lets us know that we probably cannot really use an ideal chain model realistically. So as a workaround, we propose a simple model for non-ideal chain, starting from a model proposed by Paniukov for it was initially proposed for swelling behavior, but we adapted it for also addressing all kind of force extension response. This is for the small force regime. So it still proposes a linear relationship between the force and the distance, but here the denominator is a reference length, which is the end-to-end distance that the same chain would have if it was free at the same concentration as the actual solution made to make the gel. And here, this is where we want to take into account the dependency on concentration. So what we did is basically calculate this reference length based on the overlap concentration, and then extend this relationship to any concentration. And the good news is that the exponent we have in terms of the overlap concentration is exactly the one we need to get the right scaling in terms of gyration radius versus concentration. So we could, to some extent, capture the evolution of gyration radius for the free chain as a function of concentration via a simple relationship that we use in the force extension relationship. So we have this new force extension relationship at small stretches that depends on concentration. And we have extrapolated this relationship to large deformation using the inverse Langevin relationship, so the same as for the ideal chain, matching the parameters so that at small forces it recovers this Paniukov model, and at large stretches it tends towards the contour length. So, and in between we have this extrapolation using the inverse Langevin. So this is the simple model we propose to handle the non-ideality of the chain behavior and have this dependency of volume fraction on the behavior of the chains. Regarding the network parameters, the way we created the networks to try to be representative of the actual networks is starting from the preparation volume fraction, we calculate the corresponding density of chains that the network would have if it was perfect. So if all the chains were perfectly reacted, this is the density that we would get. And that is used to set the length scale of the simulation box. And then subsequently, we introduce the defects. We keep the box size constant this time. And now we start cutting off some of the chains, and we introduce the loops. Regarding the reaction efficiency, this is a parameter that is reported in the experiment because it can be measured experimentally. So we know what is the fraction of the reacted chains, and we can use that. The only big unknown is the fraction of loops, because this one we don't know. So what we will do then is treat this loop fraction as the only fitting parameter. And I insist that it's really the only single fitting parameter we have. So what we do basically is, starting from measurements of the modulus, we calculate what should be the best fit loop fraction, and we collected this best fit loop fraction coming from a broad range of experiments, and we collect them together to see if there is a common trend emerging. Can we find a common relationship linking the loop fraction to the preparation condition. So this is an example. We started from collection of stress strain curves from experiments for these tetrapic gels. The different lines are for different reaction efficiency from 60% up to above 90%. This is for a given concentration and a given molecular weight. And this is the fitted value of the loop fraction for each case. So we had to have a different loop fraction for each P value. Otherwise, we cannot get any good agreement at all. So that suggests that the loop fraction should depend on the reaction efficiency. To go a bit further, this is just another example where people have reported the elastic modulus of gels as a function of reaction efficiency for different concentration this time. So you can see how the modulus increases when the concentration increases and also increases when P increases. So this is the reported data. And then from this data, we fitted the loop fraction with our model. And this is the best fit loop fraction as a function of P and as a function of concentration, showing that this loop fraction should increase with P and also decrease with the volume fraction, and which is consistent with the previous results. So we did that for a different set of data, well, coming from the same group of researchers, but across different papers. And we could collect data on some master curves. So here what we did is we plotted the best fit loop fraction as a function of P from different set of experiments. And here the loop fraction is normalized by the loop fraction we get when P is 1, which might be an extrapolated value. And if we do that, then we have a very nice collapse of all the data points onto a single master curve. And the dependency on volume fraction and molecular weight is all lumped within this zeta node, the loop fraction at full conversion, hypothetical full conversion. Otherwise, it's all there. So the loop fraction depends on the reaction efficiency with this relationship, which we don't really try to interpret more than that, with dependency on volume fraction and molecular weight in this other parameter. And for this one as well, we have collected different data for different volume fraction and molecular weight, which plays a role via the overlap concentration, which is used to normalize here. But anyway, it really showed that we also have not a perfect collapse, but there is a clear trend for this full conversion loop fraction, showing that the loop fraction decreases when concentration increases. And also it decreases when the molecular weight increases. Regarding the evolution of loop fraction with concentration, we also plotted the data point from this report that I've shown earlier, which is an experimental measurement, one of the very few direct measurements of the loop fraction for these systems. So we have collected this data and put them into our plots, and these are the little stars here. So these are direct measurements for the loop fraction for this condition, and it fits very well with the fitted value we got otherwise. So that seems to suggest that really both the loop fraction and the reaction efficiency affect the properties, and that the loop fraction is changing depending on the preparation condition, as you probably would expect. This is just a quick point to say that in the literature, also from the same group of people, there are arguments to try to understand the change in modulus versus volume fraction and molecular weight. And some of these arguments are invoking some transition between an affine behavior or phantom behavior. Just to say that our alternative explanation has more to do with the evolution of the network architecture as the preparation conditions are changing, especially the presence of loop can be used to explain this transition without invoking a change of regime in the way the network behaves. Just to quickly finish, once we have developed our master curves for the loop fraction as a function of the preparation parameters, we also did further confirmation. So this time we really use the master curve to predict the loop fraction. We don't use any fitting parameter whatsoever, and predict some stress strain responses, and compare to additional experimental results. So this is just 2 examples for 2 different molecular weights, different volume fractions. So we get the right trends, we get the right order of magnitude. We miss some, well, the model does not capture the broad, well, there is more differences in the curves in the experiment than what we can predict with the model. In terms of stiffening when the volume fraction is changing. So it's definitely not perfect yet, but that gives us some comfort that maybe we are on the right track. And one last point I would like to make is just talking about the scaling for the maximum extensibility of these gels as a function of molecular weight or number of Kuhn segments and preparation concentration. This is the scaling that has been observed experimentally for these gels, and this is also exactly the well, almost exactly the scaling we get with the computational model. So we can get these 2 dependencies. There is an extra correction we have in our model due to the loop fractions, but that's not dominant. So we roughly get the right scaling of extensibility versus these 2 parameters, the same as in the experiment. So that's also quite good. And that's a different scaling as the one you would get using classical rubber elasticity theory, because in that case, you would not have any dependence on the concentration, and the scaling with n would be square root n instead of n to the power of 2/3. And that's about what I wanted to say today. So as a summary, so we have implemented a random discrete network as a tool to investigate structure property relationships in these gels, starting from near ideal systems, so we don't have to worry about entanglements or physical crosslinks or these kind of things. We have a neat model system to play with. And we looked at the impact of defects on the mechanical properties, especially the modulus and the extensibility limit, showing that the reaction efficiency and the loop fraction mostly have an effect on the behavior. One of the key results really is the acknowledgement that pre-stretch, chain pre-stretch is really, really fundamental to understand the scaling relationship we got. And we think that this notion of pre-stretch is important for systems like this that are made from well-defined macromolecules in solution. Might not be the case for more vulcanized kind of network, but for network made by assembling chains with well-defined number of monomers, the way the chains are pre-stretched from the outset clearly impact the behavior. And we could reproduce some of the experimental trends with a minimum amount of fitting. Of course, we could use the same tool to investigate a lot of more different effects, where we could look into crack or fracture, chain rupture. I think the framework could be extended to accounting for reversible cross-linking mechanism. Probably need to play a bit with lamps to see how to do that, but it's probably possible. And of course, playing with the number of Kuhn segment per chain. So how the polydispersity plays a role, that could be done. Maybe also interpenetrating network. And I want to finish by advertising this wonderful conference in a wonderful city next year. So almost a year from now. The website is live. The description of the mini symposia will follow very shortly, but please book these dates in your calendar right now. And that's it. Thank you very much. I'll take your questions.
Merci, Laurence.